We're going to have a presentation on reproducible science, digital reproducible science. This is very compressed from the last time I give it. So for anybody that has questions or comments, take them at the end. If I get anything wrong, especially looking at Shell and Deepak, I'm sorry, you can correct it in the tutorial channel as I'm saying it out loud. And with that, we are going to start. So reproducible science, specifically digital reproducible science. Maybe all of us can take a thermometer out and measure the water, but what does reproducible science mean in a digital context? And we have a quick quiz time that we're not actually going to go over. And all these slides are available online so that you can look at this later. All of these links actually do light up, so you can click through and follow through to all of the sources. And yeah, that's enough time for you to look at the questions, see if you can answer them yourselves. I hope you can, at least for the first part. In the second part, you may still have some questions about by the end of the 30 minutes. You should feel good about them. And here's another word salad page, logo salad page. All of these groups are dedicated to making sure that your data are preserved, served, ready for other people down the line, other students in 10, 15, 20 years, or even yourself in 10, 15, 20 years can use your data, use your software and whatnot. At least a few of the organizers are involved in a lot of these groups. I am involved in at least 2 or 4 of them. I don't remember. And here we have a very quick index slide. This is going to be split into 2 parts. There's a science-focused section that we'll go over first, and then software-focused on reproducible science. So kind of why should you care about reproducible science? And then what can you do specifically with regards to digital reproducible science that will make your science reproducible? Hi, Shell. So reproducible science, making reproducible experiments possible. There are 3 R's in science. Everybody argues about what these words mean, because to the layperson, they all mean the same thing. There are multiple papers that define them one way, and then another paper comes out and says you're completely wrong and defines them in reverse. It doesn't really matter what terminology you're using, although I have a link to the paper that I'm using at the bottom. Really, we just want to be sure that if you were to try to reproduce your work, or somebody else was trying to reproduce your work, this is possible to do. And you're not just putting out results that don't make any sense and somebody else calls you out on it. There are 3 big things that come out of this paper, or 3 ways they try to define it, with methods reproducibility, results, and inferential reproducibility. Hopefully they all make sense to you. Yeah. Can we provide enough detail about procedures and data so that you can do the same procedures? Can you get the same results? Can you draw the same conclusions? And from then, we've also had a paper by the National Academies of Sciences, Engineering, and Medicine. And I should also mention that this is all very US focused. So if these links do not make sense to you, or terms do not make sense to you, and you're outside of the United States, I apologize for that, but my searching abilities aren't quite that good as far out. But there's a report recently released, prompted by concerns about the reproducibility and replicability of science research. What should we do in the future? How do we ensure that we can have reproducibility and replicability of scientific research? And some of the points that are particularly important to us as scientists, as people that are trying to use data and code from other people in the future are to try to fund open source usable tools and infrastructure for reproducibility. For example, you could say that this is a big reason why Pangeo continues to get funded. They're open source usable tools that people can continue to use. We have NSF recommendations related to repositories. So NSF recommends to the data repositories, the people that take your data, this is what you should try to do. You should try to make sure that everybody's data is available for people to use. And that there are tools that people can use them. And that journals and societies set progressive 3R policies for submissions. And that may not be quite happening as fast as we like. Certainly Europe seems to be much more ahead of the game than the US right now, but things are slowly changing. And yes, there is a link to the slide deck at the end. So let's take a minute to talk about the replication crisis in science. This is not just the social and life sciences where this kind of broadly came to attention at the beginning of the decade. This happens in oceanography. One of, very recently, there's a paper that came out in Nature by Resplandi about quantification of ocean heat uptake from changes in atmospheric O2 and CO2 composition. Their data is available. I've looked at it. And it just so happens that the reason that it all fell apart and a climate change skeptic who is a mathematician was just trying to reproduce the paper, and they realized that their error bars were wrong because of their splines. They're trying to do splines by hand. It didn't quite work out. And it was a problem of propagated errors. The authors have come out and said, you know, we're sorry. And when we actually do it this other way, we actually get numbers in line with what the climate change skeptic had, which just means that we have less confidence in how fast the ocean is warming. And that's okay, because this is science and it's okay to be wrong. But, you know, how do we ensure that, not that we're less wrong, but we can try to do our best and publish our best every time. And as our science uses more moving parts, from taking physical measurements to trying to put together all of the code and keeping your data in order, how do we ease the burden of using all of these dependencies, of fulfilling that we are using the best in our field to do our work? Can we use software to ensure that everyone uses the latest scientific conclusions? Do we have automatic updating of libraries? There are possibly other ways you could think of doing it. So we're trying to solve the sharing of software and data so that people aren't emailing along zip files of data and software and saying, well, you know, you have to unzip this in this directory and then type these commands, and then half an hour later, it doesn't work and you're waiting for an email response and they've already gone to sleep. So you're not going to get anywhere for another 24 hours or so. So what level of replicability is needed for software and data? Should it just be loose code? Should we take the burden off of the scientists that have done all this already and just say, here, just download this thing. I'm not going to help you with installing it. Should there be packaging around it? Should we use package managers? Should data centers have these packages available? So something like Conda. Using the Conda system to install environments. Should there be a system image? Should people just provide a virtual machine that can do everything that you need and has everything nicely installed and built? That's something we need to answer as a society, as a group of scientists, on where should these pain points lie? are current scientific best practices being followed? Are our best scientific practices of our day being followed? For all of us physical oceanographers, TOS10 is what you should be using for calculating. Not everybody does that. There are still lots of pieces of code that fall back. But really, you should. It's been out for a decade now. And it's kind of, you should. And are you using ad hoc fixes to try to make this? What happens when you can no longer make those ad hoc fixes to use what everybody in the community has agreed is the best practice of the day? What is the minimum level of fuss a user should expect to encounter? Do they need to be a language expert to know how to do their science? Do they need to be an expert in oceanography and Python and C and Fortran? Or should they just be able to get by really quickly with a simple example that they can follow? So these are all questions that, you know, are still being debated as you go through grad school and will be continue to be debated until the heat death of the universe. So we have FAIR principles. This is one of the things to try to make data easier to get at. FAIR means findable, accessible, interoperable, and reusable. So not just FAIR data, FAIR code. You could apply FAIR to just about any number of things. But it's kind of the golden rule. Can you do to others as you would want others to do to you? Can you make your data and your code easy to use for others such that others will make their code and data easy for you to use? And there's a little bit of, I guess, kind of debate about absolutes versus relatives. Is your data fair? There's a long, long checklist of what fair means. And there's like 50 or 60 points that really nobody can hit all of these points. And once you do, as soon as you do, your data and your code is no longer fair because you've missed the 61st point, 64th, 69th, 70th point that they've just added to the list. So don't worry about trying to be absolutely fair data. Try to do what you can. We are here to do science and to help others, but we're also curious people in and of ourselves. There are a number of data centers and repositories that are here to help you. And it is a requirement generally of your grant, at least by NSF, NOAA, anybody in the US, that you have to provide your data to a data center who will then archive it and take care of it for you. And they'll even give you software libraries on how to do this. So come and talk to us. I used to work for one. Now I kind of work for another one. And there are other people here that work for them. We are more than happy to talk to you and make sure that everything happens as best as possible. And there's a repository of methods for ocean best practices so that you can try to do the best you can to make your science reproducible so that you're not following some outdated manual from the 70s and trying to do something when everybody has agreed that it's time to move on. So there are DOIs for manuals and handbooks. There's a big UNESCO IOC project called Ocean Best Practices, where these things are generally submitted to them and they will publish and host them for you. They have lots of records already from previous big projects that have happened in the world. In my little section of oceanography, that is the WOS/GoShip manuals, but they accept manuals, procedures from every section of the world. They have their own little dedicated journal, best practices in ocean observing, that anybody can publish to, and a lot of SCORE working groups end up submitting their reports to. I know in my little section, there's deep sea research that will publish procedures. how to do things. I'm sure there are many more in your section of the world. And now we're going to reproducible software. And these are opinionated practices in Python, which means they're partially what the Python community thinks is best to do. Partially, they are my opinions, and more broadly, the opinions of Oceanhackweek in general, but any of them can come out and say, I do not endorse this at any time. So why spend the effort for reproducibility? You have faster deployment of your code. You have faster understanding of your code. It's easier to extend your code in the future, and it's good for you and the community. So how can we measure reproducibility? And we generally define this, I generally define this as, can you read it more than you can write it? Can you read it 1 month, 1 year from now? If after you crash, after a 48-hour coding binge and writing binge, and you wake up the next day and you don't know what the hell you wrote, that's a very bad sign for your code. Can you install your software in the future? Again, can you install it 1 month, 1 year from now? Are you able to extend it, or are you going to find all of these magic numbers and these hard-coded variables that just is going to make it so hard to work on it in the future and make you say, you know what, I'm just going to rewrite it from scratch. And then you're going to spend another month or two trying to redevelop something when, if you had done it properly the first time, better maintained for the first, and added another week onto it, you know, you wouldn't be having that problem in the future. Not to say that there isn't a time where you just need to get it done, but there's a term called technical debt about what sort of technical debt are you accumulating and when are you paying it off. So let's see about what people have said before. I'm going to peek ahead a little further. So for measuring reproducibility, I call this the time-space continuum. So can somebody else read, can somebody else do these actions where that somebody else may be you just 1 year in the future? And you may no longer be at your lab where you were a grad student, but you may now be in your postdoc appointment. And you no longer have access to the same servers, the same computers, the same anything. Can you do all of this yourself? And if you can't, you should really think about trying to spend some effort for reproducibility in the future. So these are what some people have said about software and data before. This is from the Pods Disco conference in 2018 in Hawaii. It's a recent graduate conference. So you have to have just received your PhD or be within a year of getting your PhD. And all of these ideas came from these close to finishing grad students to very early postdocs, trying to think about what the future holds for them and what are they worried about with big data. And so, yeah, these are the slides. I think I've covered or will cover a lot of these in the future. And it's just, you know, other people that you have never met are having the same problems, thinking about the same things that you're thinking, and how do we get around all of this? How can we make this easier for us to do? So how do we standardize our coding practices? At least in Python, we have opinionated guidelines. PEP 20 is one of the most notable examples. This is the way we are doing things. The more that people follow the same opinionated practices, the easier it is to share code. So if it's kind of like, you know, we could all be speaking different languages to each other, but it's going to be very hard for each of us to grab a dictionary and look it up. And you can't cop out by using Google Translate. You have to do it the hard way. But if we all are speaking the same language, or at least writing the same language, it makes things easier to understand. So we have software tools to help write opinionated Python. We have things like Conda and Conda Forge to standardize our environments so that all you have to do is type in one line and you have an environment that is ready for you to work with instead of having to try to manually install all your dependencies. We have tools like Black, which is a code formatter. And partially to that extent, it's grows towards a linter. I'll kind of explain that in the future. We have things like iSort, which cleans up your code for you. We have software tools to help facilitate opinionated Python and R. I should remember to mention R sometime in here. We have things like Git and GitHub. We have to host your data. We have Binder to host notebooks that you've been working on. And we have a project such as Sphinx in order to host your documentation, make things easier for other people to figure out how to use. And we have science decisions made by communities such as NetCDF, CF, and Pangeo. So community decisions in oceanography. We have the NetCDF format as opposed to CDF, which is another format that is completely different from NetCDF. They have different backends. Generally, we're using HDF5 or NetCDF3, unless you're using it in the cloud, which is you're probably using XAR. And if your data is not in NetCDF and is data of significant size, it should probably go towards NetCDF soon. We have older formats such as ASCII, CSV, which are easier to view initially, but as soon as you start trying to add metadata, do some tricky things with the data at great sizes, it's going to be hard. We have standard vocabularies, which are regulated vocabularies with strict definitions. Just this means that you can't use T or temp or temperature or seawater temperature all to define the temperature of the ocean. Instead, we've all agreed to use one term, seawater temperature, to define the temperature of the water in the ocean. Anybody can propose a new name. You just have to pass committee approval, which essentially is a committee of your peers. And they're there to help you get the name you need without muddying the namespace. Just because there's a seawater temperature, but you don't like it and you want to use water temperature doesn't mean that you can just propose it and it'll be accepted. If there is a good reason for using one of the other names, they will try to make sure that you know of that. We have CF, or shoot, I can't remember what CF stands for, climate forecast. Generally for physical parameters, and if you are using Xarray, there's a nice package made by Deepak called CF Xarray for this. There is the BODC lists out of the UK, which cover biogeochemical parameters and a lot more. And then we have Pangeo, which is a cloud environment, kind of standardizing environments to make it easier to run code online in the cloud. So you don't have to necessarily have a good computer or really a good connection in order to run your code. Working environments, we simplify installing and setting up an environment to run code. We've all been working with Conda and Conda Forge packages, so I'm not going to spend too much time on this. And there are virtualization, we have virtual environments that Conda provides, but there are also other tools like Docker that can do these things. Binder, a platform for making notebooks runnable online. Google has a similar platform called Colab. It allows others to try out your code before downloading to see if it actually does what they need it to do, or to even just share with other people. And it's a way to make DOI notebooks runnable. So if you have a DOI in your notebook, Binder can load it and then make it run. Version control, GitHub. Maybe everybody, I hope, most people have seen this comic before and they have probably run into something like this. If you haven't, you're very lucky. For version control, it just makes it easier to keep track of yours and others' changes. I hope everybody sees the value of that by now. it gives you the ability to have remote copies. So if your cat knocks over your coffee mug and spills it all over your laptop and your laptop is now dead, you still have a remote copy of your code that you can get to. And your commits should be atomic, which means that they're fully formed, they're not half done. Related edits are grouped into a single commit if you're editing across multiple files, and commits are small. They're one single change as much as possible and often. And just like atom in chemistry or physical chemistry, you want to keep it as small and atomic as possible so that when you have to go back and think about all of these things, it's much easier to reason about. You should be using branches to try new ideas without polluting the master. This is very important when you're working on a big project that other people are working on. And if you just start putting all your code in master, people will not necessarily be very happy with you. There are other Git tutorials. I think Stace linked to the Git tutorial I have on this link. GitHub is one of the many places hosting code repositories. You don't have to go there, but it's certainly the biggest one of them all. Code formatting, black and ISORT. So we have this very long thing that goes off the screen, and after passing it through black, it cuts it down to something that's a lot easier to read, unless you like scrolling left to right and you don't like looking down. Maybe have a really wide monitor. We have code readability. So we have doc strings. For Python, you can have these sorts of strings that you add at the beginning of a class or a function or a method. And then we have parsers that are built in order to read all of this and make very nice documentation. So if you've been looking at something like pandas or NumPy or Xarray, all of the documentation, the APIs, they're all documented like this, and then they pass it through something like Sphinx, and then Sphinx will generate the HTML version and a LaTeX version and a PDF and all of that so that it's just there for you and ready to go. You can use it with this website called Read the Docs that provides free hosting for any sort of documentation online. There are 2 themes to make it prettier, and you don't have to worry about what your documentation looks like. Read the Docs is certainly the old battle-tested standard. Sphinx Book is maybe a newer one. And for us, we try to use the NumPy flavor of doc strings. There are 2 big standards. We recommend NumPy as a science one. Code readability. Variable names. So we have context is important. So if you're only using things internally, they don't need to be as well defined or as easy for somebody to figure out from the outside, because only you're working on it or core maintainers are working on that. And some equations implemented in code can make sense to use shorter names, because even black can't save you if you have, say, 100-character long variable names. It's just going to be a mess. But these are all, for variable names, for temperature, these are all real variable names I have seen in data floating around in the wild. And we have needed to standardize on them. Some of them mean slightly different things. Certainly you can tell the difference between sea surface skin temperature versus seawater temperature. But we shouldn't be going back to temperature, temp, T. Who knows if it's actually just a temporary variable that you're kicking around, or if it actually means seawater temperature, or maybe it's the temperature of the air, or maybe it's the temperature of your sensor that you're making a measurement with. These names in blue are from standard vocabularies. Some of these are CF, CVOX, BODC. Maybe somebody should write a tool that checks files and converts standard vocabulary names between the different vocabularies. Advanced software engineering. There are many things that can be used in Python. We have decorators, factories, list comprehensions. I'm not going to go over them. It would take us another week or 2 just to cover that. APIs, Some of us have been building APIs in our projects or working with them. There are different ways to package up data as well, different paradigms for thinking about it. How do you think about your versioning scheme? Are you just going to have a 1.0 and then a 2.0 and a 3.0, or are you going to have a date version where your releases might be stamped 2020, what is it, 08, because this is 2020 August, and then next year it might be 2021 08. How are you going to version things? Continuous integration, special mention for pre-commit, which can make a lot of things with GitHub with using things like Black or linters a lot easier. Certainly when you get to a certain size, you should be using tests to make sure that when you add code, these tests are automatically run by something like pre-commit. And that makes sure that your code didn't break from a stupid change you made. Not that any of you would be making stupid changes, you're all perfect. And then there are images and containers, and please remember that sometimes better is the enemy of good. You just need to have something that works sometimes. So don't go trying to make things perfect when you don't have to be. Licensing code and data sets. There's a helpful website that you can go to, chooselicense.com. Generally, if you don't know, you don't care, you can use MIT or BSD license for your code. And for data, you can use a Creative Commons license. There is something special about USA federal government data licenses that Shell is more than happy to talk to you about, but I'm already 4 minutes over time. Publicly funded data must be open access. Data centers may license holdings. So that means if you give your data to say CCHDO, Bicodemo, and CEI, they are allowed to put a license on your data, which generally turns out to be a Creative Commons license because they're funded to make all the data publicly available. If no license is stated, a proprietary license is assumed. That means be very, very careful with what you do, that they could come back in the future and sue you. Most of the cases, the author probably just forgot to put a license on there, but it's a legal minefield that any lawyer will basically tell you, don't do anything with it, find another way to do something. And then you can make DOIs. You can make DOIs for code and you can make DOIs for data. It was previously mentioned Zenodo. You can use that, that's run by CERN. Your institution may be able to make DOIs separately. Not every institution can. There are only a few institutions that do that. So if they don't have some special license to print DOIs, just go to Zenodo. The guidelines for making DOIs for code and data are not set in stone yet. These are things I believe are still being debated to figure out what is the best way of doing these things. So this will continue to be updated as we go into the future. I'm going to leave this page as an exercise for the reader to follow through if they want to do so by clicking through on the slides. And that's it. Questions? Actually, I have a quick epilogue slide. So I've talked a lot about reproducible science, but which is kind of similar, but not the same as why make open source software. And here are just a few bullet points on why. Requirements. Your funder probably requires publicly available results, including data and software. Certainly, that can be the old days of just throwing it on your website, and that's good enough. But why stop there? Why not go further? And military-funded projects generally get around this. Certainly, the military doesn't want you sharing military secrets to somebody else. You can connect with others using the same software with collaboration. People may be using your software, you may be using other people's software, and you can lead to situations like Oceanhackweek where you learn a lot and maybe you can publish a paper or two at the end of the week and have a lot of fun. For publishing your code, all your methods, especially for computationally intensive projects, they should be auditable by others. Your code should be available for other people to look at and make sure that you're doing the right thing. And as maintainability, as your project grows, somebody may possibly maintain your software for free, like me, or some of the other people that are organizers. So if you make your code open source, I may be paid to maintain it for you, and you can do more of what you really want to do if that's science. And back to questions.